All right, guys, a lot of this is review today, but some of it is not, so please be paying real close attention so that you catch on to the new stuff. And part of what's new today is something that we can only estimate in this course, which is a struggle for students because they don't like estimating. All right, what's going on with my cursor? All right, so we're on worksheet 5. Increasing and decreasing behavior you should have done in Algebra 2. Functions can increase, decrease, or remain constant at a given interval, any given interval along the way, okay? So this graph would be increasing, and then it would be decreasing if I did this. It might remain constant for a while, then increase again, okay? So as you go left to right, increasing is when it goes up, decreasing is when it goes down, but you're going to answer in x intervals, which x intervals cause the y values to be going up or down. Okay, the points at which a function changes, increasing to decreasing, or the other way around, are called critical points. Critical points can be relative minimums, absolute minimums, relative maximums, or absolute maximums. The generic term are called extrema. It'll ask you, it might say find the extrema. It means find all the maxes and mins. And we're going to talk about relative and absolute here in a second. Here's a picture. Now, this arrow is pointing down. I need you to, everybody doing this? Martin, you with us? This arrow is pointing down. Why is the graph increasing there? Yes, as you read it left to right, okay, as the value of x increases, the value of y also increases. Okay, from negative infinity to -5, it says. Then from -5 to 0, it is constant or flat. And then over here, from 0 to the right, or 0 to infinity, the graph is decreasing. As x increases, y is decreasing. You will state the places where it is increasing or decreasing as intervals of x values. And you will use parentheses, not brackets, for these. You read it left to right again. So this graph is a picture of increasing. It's all increasing. This one is decreasing. What's this one doing? It's, yeah, decreasing here, then constant, and then decreasing again. Questions about increasing and decreasing? What students struggle the most with is they forget to give me x values in the intervals, not y values. So we'll practice that in a minute. This is a warning. It says a function is neither increasing nor decreasing at a particular point. So you never include the endpoints. It's always soft parentheses. Everybody good? Increasing, decreasing, or constant, you don't need brackets. We're going to start with this example on your worksheet, but I'd rather just practice from the picture estimating our values. We'll do a couple in a minute where we type them all in the calculator, but help me out here, guys. There is a relative maximum, okay. Relative maximum is for this graph because is there ever an absolute maximum where it stops going up? No, on the far right, there's an arrow showing it goes up forever. But there's places along the way where if I were to look at just this, there is a maximum here, and there's another maximum here. Does everybody see that? Those are called relative maximums, okay? Because they're in this section of the graph, it is peaking and then starting back down. Those occur when it changes from increasing to decreasing or decreasing to increasing. So the relative maximum of what occurs at x equals. What is the maximum y value at this one if I do this one first? Okay, the y value of 0 occurs when x is, estimate for me. -1.5 would be fine. Okay, relative minimum value of y equals what? So relative minimum would be here, or here? Which one do you want to do first? This one? What do you think the y value is? Does it hit -2 or is it like -1.8? I don't know. I'm just throwing something out there. When x is, what is the x value there? -0.5. Then there's a relative maximum. Okay, what's the y value here? -1.3 sounds fine. And the x value where that's happening is 0.5, I don't know. And then we get over to this guy, and this is a relative minimum. And the y value, does it hit this or no? Are we doing the right scale? Oh, poo. What is the scale on the y-axis? I hate these. The scale is 2s. It's 1 across. But look, this is -2, -4, -6, -8. So let's go back here. This one was right because it was 0. The minimum down here, right here, was more at -3 point something, -3.5, I don't know. Just to make us miserable. Okay, that was occurring at x equals -0.5. There's a relative maximum here. What do you want to call that one? -2.5? And at x equals 0.5. One more. What do you want to call this one? Almost -6. Does it hit there? It does hit there? Okay, good. At -6 when x equals, remember these are counting by ones, 1.5? Okay. Yikes. Is there an absolute max or min? None, because it goes down forever and up forever with those arrows on the ends, right? All right, now increasing and decreasing behavior changes at those points. Now, we use x values, so I'm going to go back and write the x values. We said, what did we say this was? We said this was -1.5, right? And then we said this guy down here had an x of -0.5. This next one we said had an x of +0.5. And the last one we said had an x of 1.5, yes? Okay, so we need to use those x values to tell whether the graph was increasing or decreasing as we went. And you start at the left. So over here, the graph is doing what? Increasing. So we write from the left, or -infinity, until what x value? -1.5. Okay. Now where else is it increasing? Can you tell me? Yes, in between these two right here. Does everybody see that piece went up again? So together with between -0.5 to +0.5 it increased. Anywhere else it goes up? Are we done? Yeah, the far right over here from, and I don't have room, 1.5 to infinity, it was increasing. 3 places where it was going up. All right, I'll use purple for going down here. It decreased in here and in here, 2 places, right? So what were the x values surrounding those 2 places? -1.5 to -0.5. And then +0.5 to 1.5. There was nowhere that it was constant. Okay, that was miserable. We don't, this is like a, let's see, 1, 2, 3, 4, 5. Probably a degree 5 or 6 equation. Well, 5 because it's, oh, duh, look up here. Degree 5 equation. I don't usually ask you to do graph analysis on a degree 5 equation. There's too many pieces to it. All right, end behavior. I would like you to describe the end behavior. We need to practice this. We haven't done this on a quiz or test yet. Go ahead.
If g of x goes to negative infinity, the x goes to negative infinity in the top, and then g of x goes to 1,000 from the x goes to 1,000 from the.
Okay. What are the words for those? The first one, y is negative, means it's going down, as x is negative, which means on the left. G of x is going up as x is going to the right. All right, well, a graphical approach to identifying the intervals on which it is increasing and decreasing are constant can be supported numerically. Calculus is often needed to confirm this behavior and to confirm that a function doesn't change its behavior beyond the domain shown. So we're just going to go with what we can see on our window, and we're going to use maxes and mins. We're not going to be proving that this works, okay? Critical values of a function are those points at which a line drawn tangent to the curve is horizontal or vertical. That's kind of crazy. Basically, our critical points are going to be the extrema, or the maxes and mins, okay? Critical points are maxes and mins. But also, critical points, when the changes from increasing to decreasing, those would be the maxes and mins. At these points, the function will have a max or min, either relative or absolute. Okay, this is the new one. A point of inflection, okay, can also be a critical point. At these points, the graph changes its shape, but not whether it's increasing or decreasing. Instead, the curve changes from being bent upward to being bent downward, or vice versa. Okay. Inflection points are between maxes and mins if the graph changes its bent. And that's called its concavity, and I will talk more about that in a second. When we do inflection points, we estimate. The only way, is that how you spell estimate? Okay. The only way to accurately find an inflection point is with a derivative in calculus. So I just want you to get used to the idea of an inflection point. Now, what does it mean? Well, when a graph is curving either this way or this way, like the halves of a smile, okay, it is called concave up. When the graph is either curving this way or this way, like the halves of a frown, it is called concave down. Now, on this graph, between this maximum and this minimum, do you see that it changed bending, the direction it was bent in the middle there somewhere? Now, does every graph change in between a max and a min? If I go back to this was all, anybody know what, let me erase all this for a second. Anybody know what this bend would be? Yes, that's all concave down. Now, clarify for me though, between this max and this min, did it change bend? It actually did, because do you see that it starts to be a happy face in there somewhere? Okay, often between a max and a min, almost always there'll be an inflection point. Okay, it has to change bend in order to change from increasing to decreasing at some point. All right, so we're going to estimate. Whoa, where did I go? where this inflection point is. So when we list critical points, it will also include inflection point, which will occur between maxes and mins, and inflection points are always estimates. So this graph, let me go back and talk about relative and absolute for a second. Does this graph have any absolute or relative maximums? Because the ends are both going down, this is called a relative maximum here, but this is the absolute max because it's the highest the graph hits, right? It's the one you would base the range on. This is an absolute max. Does it have any absolute or relative mins, the same graph? It has a relative minimum in here, and why is it not absolute? Because the arrows continue to go down. Now, in between here somewhere, guys, would be an inflection point. Is that, I wanted to use black ink. Is that black? Okay. So this is concave, what? Down. Somewhere between the max and the min, and between this max and the min, somewhere over here, it switches, and this piece is concave up, and then it switches to concave down again. Okay? Looks like a little man, right? Or something. Yes. This one, what's going on here? What is this point? Relative minimum. This one is a absolute min. This is a, yes, go ahead. You sure? Because it doesn't ever go lower than that, right? This is a relative max because according to these arrows on the end, there is no absolute max. Now, I'll say that, and I'm not going to ask you on the quiz if it's relative or absolute, okay? It'll just say find the maxes and mins. All right. Calculus is needed to confirm increasing and decreasing. It's also needed to confirm relative and absolute extrema. For now, you're just going to use your graphing calculator. This little hint, though, just says be real careful. Be sure you zoom in or out enough to make sure that you're seeing the whole graph and the whole story of the graph at a point. Okay. So here we go. We are going to put this in while you're typing that in, because I think I actually have it ready to go today. I know it's a miracle. Is that it, guys? 2x to the 6th plus 2x to the 4th minus 9x squared? Okay. I'm going to go down and turn this one off for now and leave the blue one on. Okay. It says, use a graphing calculator to approximate to the nearest hundredth the relative or absolute extrema of each function. Include a sketch, with window that should say. State the x values where they occur. Also state where the graph is increasing or decreasing. Estimate where the graph is concave up and possible inflection points, up or down. Okay, also we're going to talk about end behavior. So we got a lot of stuff to write down. If I do a zoom 6 for this particular one that we're supposed to be working on, good window, bad window, how do we know? It's not bad. I would probably change it a little bit, but it's an okay window. How do I know that it doesn't come back down somewhere? I could go out further. Does anybody know anything about a degree 6 equation? It could have up to 6 zeros or 5 turns. I don't think this one does because of, you can take out an x squared, okay? But a positive leading coefficient with an even degree means both ends should be going up. So we are seeing that both ends going up. We could talk more about if we took out an x squared, it's doing a bounce here. So that's 2 of the zeros. There's 2 more. Yeah, we're just going to be done. The only thing I would do to make the window a little better is I would change the x, because we had a lot of space on both sides. I'm going to go like -5 to 5, so that when I look at the graph, it just seems a little smoother here. All right, what points do I need to locate?
The center point at the 0 and then
It looks like that is a center point, but what am I supposed to be locating?
relative minimum.
Yes.
Absolute max.
So what would you think that one at 0, 0 is?
The max.
A maximum? Okay. So I'm just going to type in between -1 and 1. Where's the maximum? Oh, that is garbage. But what does that mean? Do you notice the e to the -6 and e to the -11? Did anybody get a way better answer than that? It's 0, 0, right? If I do it again, maximum, and I scroll to the left a couple, hit enter, scroll to the right a few, hit enter. Yeah, I still have a hot mess. But it's 0, 0, right?
Maybe you guys put the center thing and put yes. Maybe just do it.
I could guess 0, 0, and it might help. I don't know. But, okay, so we're supposed to show a sketch. Let's put my graph on here. Ah, stop. We're supposed to show a sketch, so you guys sketch it real quick, and I'm going to label that point 0, 0. And what else do I need to label for extrema? Or maxes and mins? I need to find these two minimums. Okay. So I go back to the calculator, and I do second trace minimum. One of them looks like it's over to the left here. I would say between -2 and 0, but you can cursor around if you like that better. -0.967, anybody? Is that exactly what you're getting? Yeah, -0.967 and -5.031. Did it say? It said hundredths, so we only have to do 2. So that's actually negative, what is it? Point. Thank you. And the y value, okay, so over here I'm going to write there is a relative min at -0.97. And what was the y value there? -0.30? Oh, 0.3? Anybody? What is it? I don't... Yep, -5.03, okay. And is there another minimum? Okay, I'm going to find the other one. Now, I purposefully, on my picture, only wrote the x value. There is another minimum over here on the positive side, somewhere between here and here. And I get 0.967 and -5.03. Does that make any sense to anybody? This certainly looks like it has what kind of symmetry? Y-axis symmetry, which would make it an even function. Very good. So there is another one exactly the same distance to the right of the origin. Lost my cursor. So positive 0.97 and -5.03 was also 1. And there was a maximum, relative maximum at 0, 0. Okay. How about increasing and decreasing next? As I trace the graph left to right, remember that's the important thing for increasing and decreasing. As we go left to right, it's first going what? Decreasing, then it's going increasing, then it's going decreasing, then back to increasing. Okay. So who wants to tell me the intervals where it is decreasing? X values.
-30 to positive -0.97.
Good job. Anywhere else that it's going down?
From 0 to 0.97.
Excellent. And where is it going up or increasing as we go left to right?
-0.97 to 0.97.
Yes, you are right. I wrote it down wrong. 0.97 and to the right. We okay? All right, then we get to the icky stuff. They want to know concavity. So we need to estimate inflection points in between there and there. If I go back to my calculator, somewhere in between this minimum down here and this maximum, I need to find, what do you want to pick? -3? What were the the x values, guys? 0 and -0.97, right? What's somewhere in between there? -0.5 or something? Okay, so if I type -0.5, that's what I'm going to put down as my inflection point. I am estimating that the inflection point is, please make sure you're on the actual graph, not just tracing around in the middle of nowhere. That's why I pushed the trace button and typed in a number. So inflection point, and anybody tell me what it was? We went to the graph, and do you see it was curved up here, concave up like a happy face, all the way until it's always somewhere in between the maxes and the mins. So this was a min, and here's a max. So somewhere in the middle is a inflection point. It's not at the exact middle. It has to do with calculus to be able to find the actual value. So we are just estimating. And because it was somewhere between -1 and 0, we estimated -0.5. Typed it in and got -2.09. Now over here, guys, it goes from 0 to +1 almost, right? So can we try 0.5? If we type trace 0.5, we still get -2.09. So our other inflection point we are estimating is at +0.5, -2.09. All right, then this is the tricky part, concavity. Oh, and we still need to do end behavior. These take so much time. Okay, concavity. Concave. What did it start out on the left? Yes, all of this is a happy face until we get to that inflection point. So concave up from -infinity until, what did we decide the x value was at our first inflection point? -0.5. Okay, and then it flips. I'm going to use my yellow highlighter here to show where it's sad, right? Is that a frowny face from there over to here? To the next inflection point. And then it's happy again from this inflection point on this way. It's curving up. The concavity is up. I know this is tricky, guys. Yep, from 0.5 to infinity, it's up again. Okay, so where was it concave down? From -0.5 to +0.5, because it was in between the inflection points. Okay, so you might want to make yourself a note. These two values, concave up and concave down, use whatever you used for your inflection point, x value again. Okay, they have to be the same. If you pick an inflection point And then you can't tell me it's concave up and concave down somewhere else. It has to use those inflection points. Okay, end behavior. Anybody good with end behavior? What is this doing on the left? Yes. And as x approaches positive infinity on the right, it is also going up. Yes? Okay, did you manage to fit all that garbage on there? Barely? Okay. All right, one more. Number 2. Number 2 is different because it's not an even function. I'm going to go back to my standard window. Oh dear. Does anybody else get a really bad window? Okay. No, what do we need to do? Do we need to go further left? We probably don't. We could go a little further left. Do we need to, I think we need to cut off a little on the right, probably. So I'm going to change my x to like -12 to +4 maybe is enough. That looks okay. What do I still need to do though? I need to go way up, which is which value? The y maximum, isn't it? Okay, is 50 enough? Nope. 150 is enough? Okay. Now, by starting where we did though, where we zoomed out enough to see that it wasn't doing anything crazy, either of those, at this minimum, there was no hidden, it wasn't like doing a little tiny loop-de-loop there, right? Before we zoomed out, it's all a smooth curve because it's a degree 3. There's at most 3 places that it crosses. But if I were to go back, did it cross twice down there? I can't remember. Or did it bounce? I don't know. Let's see what happens. Because we should be able to tell when we do what? We could find the zeros. We could also find the minimum. What is this minimum, guys? 0, 0. If I go to the left, oh, the y is negative, isn't it? It is below. No, I wasn't on the graph. I wasn't tracing. We should have had this discussion before we zoomed in. Or out. Is it ever, if I trace along here, is it ever crossing? Yeah, it just stays positive. It bounces. Good call. And how do you know that? By the graph. Does anybody know by the equation how that it bounces? Because you can take out a what? An x squared. That means it's doing a bounce. Okay.
So is the amount of x squared did you take out the amount of bounce?
What did I change the window to? Okay, there goes half an hour of our lives. Well, Hofbauer tries to get the window again. Okay, so there was a minute 0, 0. Where was the max at?
-6, 108.
-6 and 108. Okay. Where do you want to estimate the inflection point is then? Somewhere between that max and that min, between -6 and 0, -3. So we're going to use -3. And if we trace and then do -3, we get 54. Okay, I'm going to put my little sketch down here. And this point had an x of -3. This point was a max at -6, 108. And it had a min at 0, 0. So this was at -6 and this was at 0. I don't like to write the y's on my picture because then I start writing y values down when I do intervals. All right, what else are we supposed to do besides max and mins? Increasing. Where is this increasing? Negative infinity to -6, it's going up. Then it goes down all the way to 0, right? And then from 0 to the right, it's going up. So where's it decreasing? -6 to 0. We always use parentheses on those. Okay. Then we had the inflection point. We estimated was -3. What did it give us? 54, guys? Okay. That's weird because it usually doesn't come out exactly half of what this is, just so you know. But it just happened because of the symmetry of the graph to come out half. Now, what was it doing before the inflection point? All of this was concave down. How many of you have no idea what that means? Concave down. You all good? It means if I trace it out, the little face is sad, right? Then from here over this way, it's happy. So this was negative infinity to -3, and then concave up from -3 to the right. How am I doing on time? Not so good? Okay. Do I need to do end behavior? Can I skip end behavior? Okay. We're getting there on that. Okay. This time I was just going to estimate. What is the thing that's really giving you trouble? Usually it's the inflection points, yes? So just on this one, because it's an estimate, I don't want you to type it in. Just put a dot here. What do you want to call that dot? I'm not sure it's at 1, but like 0.8, -2. And 0, 0. And this one down here, 1.2, -4. So this was the inflection point. So do we need to practice more concavity? You want me to skip the rest of this? Increasing, decreasing, what's giving you trouble? This would be concave what until the inflection point? So it's concave down, pretend I wrote that right, from negative infinity to the inflection point of 0.8. And then it's concave up. All right, we have one more thing to talk about. And oh, we didn't get to do this application, a box problem. Maybe it's Monday. The other thing that's on the homework, guys, is not a box problem. It's average rate of change. Do you feel like we've done this before? Okay, just quick review. Number 5, you're supposed to find the average rate of change in here. That means you put -3 in and you put -2 in. Look at what Hofbauer did. Look right here. Put in -3, you get 29. You put in -2, you get 1. Okay? I did it ahead of time. Then what do you have to do to finish the problem? Yes. The average rate of change is 29 minus 1 over -3 minus -2, which would be 28 over -1 or -28. And then number 6, they would want you to put in a 1 and a 3. And I got out a -5 and a 47. So 47 minus -5 over 3 minus 1 is 52 over 2, or 26 positive. Okay. The assignment is on your homework check sheet, but don't follow the directions in the book. The first 3 problems, it says you need to sketch and give me your window. You need to find the maximums, the minimums, where it's increasing, decreasing, concave up, concave down, inflection point, and end behavior. For 3 problems, okay? And then the last 3 are, or the 35 and 37, I think, are rate of change, and I don't know what 47 is. So 6 problems, but 3 of them are a little bit of work. But you need to practice this. The answer key is in Google Classroom. 1.3 answer key had a mistake, and Ms. Abruzzo fixed it in Google Classroom. If anybody was working on that and checked it and was like, I ain't getting that answer. Somebody told her it was wrong and they fixed it. I don't know what problem it was. Any questions? Okay. Fabulous weekend, guys.